multi-level hierarchy that provides insight into the region's connectivity using a probabilistic model. For more specific details, come to my talk.
We present an interface to visually analyze and steer zero-shot learning models. Our interface is designed to diagnose attribute mispredictions to convey potential failure modes in zero-shot learning. Using our interface, the user can select multiple categories for analysis. We allow the user to steer the model by changing the weights of potentially problematic attributes based on their analysis.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. Connect to the data you care about. Sort, highlight, drill down, or filter your data in seconds. Add calculations to extend your data. With Tableau, you can keep on asking questions in the data until you discover the root cause. Tableau. Answer questions at the speed of thought.
We present a high-quality tube rendering method for 3D line datasets. GPU-based raycasting is used to render line segments as rounded cones, to allow for smooth connections along individual lines and variation in radius. We support transparency by a novel approach combining visibility order rendering with an order-independent transparency method. To improve depth and feature perception, ambient occlusion is employed.
Blockchain has gained more attention and its applications are emerging. We collect 76 blockchain visualization tools and systematically classify them into 5 aspects: target blockchain, blockchain data, target audience, task domain, and visualization type. In the end, we look at open challenge in blockchain visualization.
Visualizations are about visual patterns, but there's more, much more. We show the connections between more than 100 arguments on why visualization works. And don't forget to check out our website.
Traditional clustering tools do not include users in the analysis loop. We present PK clustering, a new approach for interactive clustering using VIS. First, users specify their prior knowledge. Several algorithms are run and match with the prior knowledge. Users then build a consolidated clustering iteratively with suggestions based on consensus, the graph, and their knowledge of the data. The result is a consolidated clustering.
We present a framework for the visual exploration of spine simulation data. We show the force distribution on spinal discs, enable assessments of imbalances, and reveal impact vectors that were not accessible before. This is a novel direction in medical visualization, and we hope that it might bridge the gap between biomechanical research and clinical application.
Hi everyone, I hope you're doing well. I'm Haekyu Park from Georgia Tech. I'm very excited to present Bluff, a visualization tool to interactively decipher adversarial attacks on deep neural networks. Deep learning is now commonly used in many domains. For example, in the medical field, deep learning models can estimate the treatment effects on patients. On the road, we can see self-driving cars using computer vision technologies. However, deep learning models are vulnerable to adversarial attacks. An adversarial attack applies carefully crafted perturbations on data inputs and fools a model into making incorrect predictions. Adversarial attacks jeopardize many deep learning-based technologies, especially in security and safety-critical applications, such as data-driven healthcare and self-driving cars. Due to the threats of the adversarial attacks, people cannot confidently use deep learning models. To overcome the vulnerability of deep learning models, we need to understand how the adversarial attacks permeate the model's internals. Also, for a better understanding about adversarial attacks, it would be worthwhile to examine if and how an attack strength changes how the model produces incorrect predictions. For example, it would be useful to know if a stronger attack exploits the same neurons as a weaker attack does, or if those sets are completely different. We present Bluff, an interactive visualization tool for discovering and interpreting how adversarial attacks mislead DNN into making incorrect predictions. Our main idea is to visualize activation pathways within a DNN traversed by the signals of input data. For given input data, an activation pathways consist of neurons that are highly activated and the most influential paths. Activation pathways represent what features are detected and how those features are related to contribute to the final prediction. To understand how the attacks manipulate the neurons and the paths inside the models, Bluff visualizes the activation pathways of both benign inputs and attacked inputs. That is, Bluff finds and visualizes the most activated pathways given benign and attacked input data. Bluff also visualizes the most inhibited paths by the attack to uncover where the attack is blocking the signals to the benign path. Also, Bluff visualizes the most excited paths by the attack to uncover where the attack stimulates to induce the activation pathways going towards wrong directions. The Bluff interface tightly integrates three coordinate views. It consists of control sidebar, graph summary view, and detail view. Here, a user inspects why a deep learning model misclassifies adversarial giant beta images crafted by the projected gradient descent attack as armadillo. In the main graph summary view, we visualize the activation pathways of benign and attacked input data. Here, each vertex represents
Great. Good morning, everyone, or good day, or good evening, good afternoon. So today we have this visualization for machine learning short paper session. It's going to be quite a long session with like 9 papers, so we have quite a lot ahead of us. So I guess let's get started right away. The first talk will be visually analyzing and steering zero-shot learning by Saroj Sahoo, which will also be talking. So, good.
Hello everyone, I'm Saroj and I'll be presenting our work on visually analyzing and steering zero-shot learning. Given the task of object recognition, most of the traditional machine learning algorithms are based on supervised learning, wherein we provide the model with lots of data along with proper annotations. So given data X, we divide it into train and test set. The objective is to learn a mapping from X to Y, where Y is the set of categories. The problem with supervised learning paradigm is that it requires lots of training data. More data means more annotations. This can be costly in terms of both time and cognitive load. Moreover, these models cannot recognize objects they have not been trained on. Thus, to overcome all these challenges, we have the problem of zero-shot learning. In zero-shot learning, we train a model to recognize objects not seen during the train time. So, if the train set contains a set of categories S and the test set contains a set of categories U, then S and U are disjoint. The objective is to learn a mapping from X to U. Since training and testing categories are disjoint, to solve the problem of zero-shot learning, some additional side information is necessary. The side information is usually a high-dimensional vector space wherein both the seen and unseen categories lie. In most cases, human nameable attributes are used as side information. For example, suppose we have a category zebra. Then the attributes like black, white, stripes would describe the category. Typically in zero-shot learning, we provide the model with an input image and get a predicted attribute vector as output. The image is then classified based on the similarity score between the actual category attribute vector and the predicted attribute vector. So where can the predictions go wrong? Let's say while training, the model encounters two categories, bobcat and Siamese cat. These two categories share some common attributes like furry and paws, but they can be distinguished by attributes like fast and domestic. Since we are transferring knowledge from seen to unseen categories, it is possible for the model to mispredict certain attribute value and thus resulting in wrong classification. For example, it is possible for the model to underpredict the domestic attribute of Persian cat and confuse it as a leopard. Keeping these issues in mind, we design a visual analytics system that can help us understand zero-shot learning in terms of what categories it can predict correctly, what categories it tends to predict incorrectly, and for those incorrect predictions, why the model made its decision. We allow the user to analyze and then modify certain aspects of the model to mitigate error downstream. To summarize all the categories, we present a scatterplot view to the user. The scatterplot is obtained by using t-SNE on the category attributes. Thus, the points that are closer to each other have similar set of attributes. In order to visually diagnose predictions made by the model, let's look at the max margin loss. Consider a single instant of xi. Then we have in equation 1 a function s, which is the dot product similarity. And we are trying to maximize the margin of compatibilities between the ground truth vector yi and all other seen categories y. When the model mispredicts, the term py of xi is rendered positive, indicating we are either underpredicting or overpredicting an attribute. More precisely, when f of xi is greater than 0, we are overpredicting. When f of xi is less than 0, we are underpredicting. To visually explore the seen categories, we take the misprediction scores captured by a py of x for each of the attributes. We use a stacked bar plot where the individual bars are the categories selected by the user. A sequential color map for a fixed hue of red and blue is used for over and under predictions. To analyze unseen categories, we use the category attribute vectors, allowing the user to relate to the errors made by the attributes on seen categories. When the user selects a single unseen category, we place a length-encoded bar in the center. But when the user selects exactly two unseen categories, we layer the bars on top of each other. When the user selects more than two categories, we treat this as a case of analyzing category overview and encode categories using ordinal color map, where we map the total number of classes that overlap in a particular attribute to a grayscale value. We allow the users to reorder attributes to help find visually salient patterns. We allow ordering by over and under predictions, sum of over and under predictions, and sum of unseen category attributes. Next, we allow the user to change the weights of the attributes that are potentially problematic by clicking on the attribute bars. Let's go through a use case scenario of our system. First, the user selects a subset of categories. In this case, it's moose, ox, and deer. Then the user selects unseen categories like sheep and horse, which are close to the selected seen categories. After the unseen category attributes are populated, the user orders the attributes by underpredictions. Here the user observes that sheep are weaker and smaller than horses, and for these attributes we observe high underpredictions over related seen categories. Thus, there is a potential to incorrectly classify a horse as a sheep by underpredicting strong and big attributes. Now, the user orders the attributes by sum of unseen attribute values. The user finds that the attribute brown is highly overpredicted and horses are generally more brown than sheep. Thus, the model is likely to mispredict images of sheep as horses on the basis of the attribute brown. After identifying these unreliable attributes, the user steers the model by decreasing the weights of these attributes. Upon retraining the modified attribute with the modified attribute weights, the user can see an improvement in model accuracy. We think that our approach is an important step in using visual analytics to help understand zero-shot learning. In general, we find that localized analysis applies quite well to unseen categories, and in most cases the results are quite encouraging. But one potential downside is that an improvement in one category might result in a decrease in accuracy for another category, leading to potential bias. Global analysis of unseen categories can help counter such bias, thus a mixture of these two analyses is most likely to be useful in practice. There are several directions we would like to explore as part of our future work. We have thus far only considered our approach for animals with attributes dataset, and so we intend to use our interface for other zero-shot learning datasets like the cub dataset, and we expect our interface to scale fairly well for it. But for larger datasets, will necessitate like different visual encodings and interactions. Thank you.
Great talk. Yeah, so I see there's a couple of questions coming up in chat. And so we have a little bit of time to go through these.
Hello, my name is.
So the first question was, how does the user manually change the weights of these features in a deep learning model?
So you do not change the weights of the features, you change the weights of the attributes, which are like human enableable. So when you identify a potentially bad attribute, you click on the bars, and that would decrease the weight for that particular attribute. And then you can use those weights later to retrain the model and get an improved result.
Okay, sounds great. So the next question is, where do these attributes come from? It seems that it relies on fuzzy attributes, which are harder for a machine to classify than a human.
So these there are different ways in which these attributes can be collected. So in like most of the times it happens like a group of people have some name some attributes, and then they assign some values to it. It can be like a continuous value or a 0 or 1 value. For our case, we are using a continuous range of values. Yeah.
Cool. And so the last question, I guess we have time for that. Can continuously adjusting the weights based on discovering problems lead to an overfitting of the model? That is it, since we are adjusting them manually, right?
Yeah. So so there is a potential. Means like if if we want, we can potentially overfit the model by changing the weights over and over again. So that's why I mentioned, like, when we are doing a local analysis, we have to make sure that we are not biasing our model towards a particular category.
Okay, yeah, that is, yeah, overfitting is always a topic that we need to keep in mind. Great. Okay, cool. Thank you very much. And I guess we can move on to the next talk, which is DRIL, Descriptive Rules by Interactive Learning by Fang, Eli Brown. And presenting will be Eli Brown.
Hello, my name is Fang Chau, but you can call me Caroline. Just don't call me Fan. I don't bite. I'm a PhD student working with Eli Brown at DePaul University in Chicago. This presentation is about our short paper DRIL, Descriptive Rules by Interactive Learning. Everyone needs to make decisions with data these days. These data workers are not necessarily data experts. We need to understand the data, but they don't have the right tools. In this work, we started thinking about how people might actually want to explain what they found. There has been emphasis on this in the past, often using linear models. Linear models are easy to explain relative to something like a neural network, but they are not very natural. For example, explaining that you need to look 0.7 at variable 1 and 0.09 at variable 2 is not the way humans communicate. This led us to create a simple mechanism that automatically learns rules to describe data. Rules can explain, for example, variable 1 should be less than 2, while variable 3 should be greater than 10. We can see not only which variables are important, but what ranges of values. In fact, going back into AI literature, rules have long been studied as models for human problem solving. Figuring out exactly what rule describes your data by hand is difficult and tedious. We propose a human-in-the-loop system where a user guides automatic rule learning. Given a selection of data points of interest, the system provides an interactive visualization of rules that describe how those data are different from the rest. The user can interact with the rules and data selection to deepen their understanding and continue the interactive loop. We chose an existing rule learning algorithm based on experiments. The paper's related words section describes more alternatives. The user task is to characterize or describe data. But the algorithm is a machine learning classifier. The key to using a classifier to support this task is to have the classifier predict whether a point is in the user selection or not. Therefore, the rules it produces will explain how the selected data are different. The rules that the algorithm outputs are not ready for non-experts to read. After a few edits we described in the paper, they can be visualized. The user can see the rules and thresholds with the data distribution for context. We built a prototype system DRIL that shows how our interactive descriptive rule learning works. It provides basic visualization tools for exploration and point selection, a button to learn descriptive rules, and interactive rule visualizations for exploration and iteration. We use a use scenario to demonstrate it. Our usage scenario follows Frankie, who is a manager reviewing a dataset on absences from work. She has data for each absence, including who missed work and why. Not knowing a specific place to start, she simply uses an MBS projection and colors data by the length of absence. There are multiple apparent groups, and the darkest points in one group on the upper right, so she starts there. DRIL made this type of sense-making trivial. She simply selects that set of points and clicks a button. In response, a set of rules describing those selected data points appears to the right. DRIL has identified an interesting pattern. These absences are during the fall and winter and by people who identify as social drinkers. She wants to explore more, and she mouses over the rule at the button that says non-social drinkers are not included. The corresponding highlight shows all non-social drinkers. She can see this variable clearly separates one half of the data from the other. She can also see not only the season is an important variable, but also this group of absences is best explained by the specific value fall and winter. She has been able to quickly develop a hypothesis that these absences are people getting sick from social gathering during flu season. Of course, she will need to further investigation to confirm. Our machine learning experiments are not meant to evaluate the algorithm, which is already established. We evaluate it in this interactive context. The experiments show how it works with a small amount of labels because the user chooses a small number of points. We also choose metrics meant to match. Recall measures how well we were able to capture all the selected points with the rules. Inverse recall measures how well we capture the non-selection of the rest. It's important to know that this model should not actually be used for prediction. The class imbalance is typically large due to the user selection size, so the accuracy is not meaningful. The recall and inverse recall, however, show that user selection can be described effectively. Thank you very much. We'd love to take more questions.
Very, very great talk. Yeah, and as we're not there. Okay. Great talk. And thank you very much for presenting. Even though you're not here, congrats on the baby. And yeah, so the questions will be answered by Ellie.
This is, yeah, I'm not exactly Caroline, but.
Yeah. Okay, so far I don't see any questions in chat, so please add more questions there. I have a question in the meantime. So you're basically establishing those rules, and my question now is, when somebody without like much machine learning background looks at this UI and looks at those rules, could it happen that they kind of like misinterpret the significance of a rule, right? Or like weigh it more higher than it actually should, or like draws conclusions like correlations that are spurious and not actually like defendable. So is there a way to defend it?
Excuse me. Yeah, I think that you know, there's kind of a risk with any tool that sort of tries to bring people quickly through the first parts of sense making, right? If the tool is too easy to use and gives you ideas about the data too quickly, then there's always room for bias. But in a work like this, we're trying to bring in this idea about using rules to explain data. And so, I think it's explained in the paper as an exploratory tool. As a lot of this type of work is, this is a way to quickly get a handle on what might be interesting in your data. And you don't want to ever draw a final conclusion from your exploratory analysis.
Absolutely. Yeah, thanks. I see there's another question coming up. So the question is, I wasn't exactly clear on what the rules exactly look like. Are there like a decision tree where one attribute is squared at a time, or is it like, how do the rules look like?
Yeah, good question. So the rules are coming from a decision tree from the C 5.0 algorithm of Quinlan, but it actually derives rules from that with some other optimization for rules as opposed to just all the paths through the decision tree. So they look basically like that. You query one attribute at a time, but you can have more than one attribute represented as a rule. Excuse me. And so that means, all the interactions where you look at what data points correspond to a rule correspond to those multi-attribute rules. So there could be one or two at a time.
Okay, great. So I see a third question in the chat, but we are already running a couple of minutes late. I'm sorry. So if you would just stay in chat and answer any further questions in
of course,
chat,
thank you.
That would be great. Thanks. Okay, awesome. So coming up is the next talk, Vortex boundary identification using convolutional neural network, and the presenter will be Marzieh Berenjkoub.
Hello everyone, today I'm gonna present our paper Vortex boundary extraction using convolutional neural network. This work is a collaboration between University of Houston and FLU Erlangen-Nuremberg. This is the work done while I was a PhD student at the University of Houston and I'm now employed at NVIDIA. Here is the outline of my talk. First, I introduce the problem and motivation of this work, and then I describe our method and go over some of the results. Vortex dynamics plays an important role in determining the behavior of fluid flow across a wide range of Reynolds number, ranging from laminar to highly turbulent regimes. They are easy to observe around us. For example, these are the vortices in the Atlantic Ocean, or the wing top of the airplane, or in the blood flow. There are two most recent methods that focus on a vortex boundary extraction. The first one considers the vortex boundary as barriers to diffuse vorticity transport in two-dimensional flow, and the second one considers the elliptical Lagrangian coherent structure as a vortex boundary. However, there is no unique definition of the boundary. Region-based vortex measures are commonly used to extract vortices. The ideal threshold to extract vortex boundary, however, varies especially. To detect vortices without manually thresholding, we utilize supervised deep learning. Our method is divided into two parts. The first part, we used a parametric mixture model for vector fields in order to synthetically generate the vortex patches. And in the second part, we use deep learning in order to extract the vortex boundary. Here is the pipeline of our method. In the first part, which is synthetically generation of the steady flow, we are trying to synthetically generate these vortex patches and the velocity data. Later, this velocity data will be the input of our neural network. In order to synthetically generate the vortex patches, we use Batista's velocity profile. In Batista's velocity profile, we have two parameters, RC, which is the radius with maximum velocity, and define the boundary of the vortex, and N, which is the shape exponent, and define the shape of the velocity. To introduce variation to the location, orientation, and size of the vortex, we define a random linear transformation matrix A and a random translation vector T to transform the domain and accordingly transform the velocity and distance field. To control the shape of the deformed vortices, we compose the linear transformation to a rotation and a non-uniform scaling matrix. Therefore, we have 7-dimensional parametric model for a steady flow primitive. Here are some examples of 2D steady flows that we generated with this vortices model and with our parameters. However, in order to detect vortices in numerical flow, we need to generate vortex patches that are very close to the vortices in numerical flow. Therefore, we try to optimize the parameters of our model. We extract 32 by 32 patches from numerical data and use simulated annealing to find the set of optimized parameters. Here is the results of our parameters after optimization. As we see the histograms of individual model parameters showing near Gaussian distribution. The second part of our method is using supervised learning in order to do binary classification of the vortex and non-vortex area in the patch. We try on 3 different network architectures. We use CNN with 2 convolutional layers and 2 dense layers. We used ResNet32 and we used UNet with 3 levels of depth. Let's look at some results. Here is the vortex boundary extraction results on the test sample. As we can see, UNet could generate a smoother boundary and a closer boundary to the ground truth. And those are the results of the different architectures on numerical flow. Again, we can see that UNet could beat the other 2 networks. And also, we can see that in comparison to IVD, which is a threshold-based method, UNet could generate a better boundary and a better vortex at the end part of the cylinder flow. And also, in the beginning of the cylinder flow, we can see that UNet could identify the small vortices at the beginning and near cylinder much better than IVD. Numerically, UNet also could generate a better matrix in true positive, true negative, false positive, and false negative in comparison to the other network architectures. And finally, we compare our timing between these 3 network architectures. And we can see that UNet, although it has a training time double of ResNet, but still it can have the same inference time, which is good. To summarize, we propose the deep learning method to identify the vortex boundary. The results show that we got improvement in comparison to the threshold-based method. In future, we are going to extend our method and remove the dependency to the specific set of parameters. We thank the anonymous reviewers for their valuable feedback, and this research is supported by NSF and Swiss National Science Foundation. Thank you for your listening, and I'd be happy to take any questions.
Great talk. Yeah, so it looks like we have some questions in chat. So let me start right away. So you mentioned the UNet worked best for you, and here the question came up whether a SOTA image segmentation model would work even better than that. Did you thought about that?
Yeah, it's kind of similar to the segmentation, to the image segmentation, but the data for that we are like adding as an input is like the velocity data, and the value is like the distance field. So based on the distance field, we did a binary classification. So it is not exactly like an image classification. It's mostly similar to the regression method, but kind of close. But it's still, it's like we need like multiple data as an input, and the target is just a value that we we ourselves did the binary classification, apply the binary classification on that. So it's a little different from segmentation.
Sure, great. So the next question is, input data are pixels or velocity? Oh, I guess you answered that, right? So it is mostly velocity, and yeah. So the next one is, how are you handling moving vortices? Does your method only work? Oh, well, okay, one question at a time. How are you handling moving vortices?
At this moment, actually, we are working on the steady flow, and we are not considering like the time-dependent flow, and it's just we consider only one-time slice. But I think if we want to handle like timing, it's just we need to add like more data input to the neural network, and then just track the center of the vortices. So it shouldn't be like that difficult. We can add it in the future.
Sure. So does your method work only, well, in local steady reference? Okay, yeah, that's also, I guess, already answered with that. So yeah, like you are only looking at the steady reference frame right now. Do you only use the velocity fields, or do you consider higher order flow properties as well?
At this moment, we only used velocity field, and our training data is just based on the synthetic model of what is this model, and so the output is just velocity. So we didn't consider any specific feature, other parameters or features.
Okay, great. And how would you generalize to flows apart from vortex streets?
Actually, that's a good question. So at this moment, our training data, our model is like highly dependent on the training data, and we are trying to like generalize our model and like remove this dependency to the parameters. And we think that if we like inject enough input data with different like behavior of the vortices, we can remove this dependency. But this is like a part of our future work.
Okay. Sounds great. Thank you very much for answering all the questions. Should any questions pop up in chat, so maybe it would be nice to stick around, I guess, if anything comes up more. So let's move on to our next talk, which will be, how does visualization help people learn deep learning? Evaluating GAN-lab with observational study and log analysis. And the presenter will be Minsuk.
I'm Minsuk from Oregon State University. In this talk, I'll be talking about our evaluation studies of GAN-lab, which is an interactive tool we developed for people to learn about a deep learning model called GAN. Visualization has been successfully helping not only experts, but also people who want to learn AI. TensorFlow Playground, GAN-lab, and several articles on this tool are great examples. In 2018, we developed GAN-lab, the first interactive tool for learning GANs, generative adversarial networks, one of the very popular but hard to understand deep learning models. It was developed in collaboration with Google People Plus AI Research Group, and we presented a paper at VIS 2018. The work I'll be presenting today is a follow-up evaluation study of GAN-lab. So let me first briefly tell you what GAN-lab is about. The main idea of GAN-lab is enabling users to interactively train a GAN model on their browsers, and the tool effectively visualizes the complex dynamics of the model's training process. So by using the tool, users can actively learn about GANs. Let me show you a quick video demo. Users can first draw a data distribution for a GAN model to learn. Specify hyperparameters such as the number of layers, and then start training a new model. Then the tool nicely visualizes the inner workings of the GAN's model training process. In addition to that, users can dynamically adjust hyperparameters while a model is being trained. For instance, they can change learning rates to see how it affects the model training. With this type of interactions and visualizations, users can playfully and actively learn about GANs. GAN-lab was a great success. More than 130,000 people over the world have visited our website that has a live system which anyone can visit and use. It was possible because our system fully works on web browsers, which means users do not need to install anything other than browsers. While we are very excited about it, we also wondered if these visitors are actively engaging with GANLab and wondered what they learned from it. Interactive educational tools like GANLab have gained popularity and research interests, but there has been little work in evaluating these tools with human subjects. So in this work, we designed and conducted 2 evaluation studies. First, we conducted a small observational study to investigate how our target users would use GANLab. Second, we collected and analyzed 20 weeks of interaction log data from visitors of our live system to study whether they are actively engaged with GANLab using a variety of features it provides. As a first step, we conducted an observational study. We recruited 6 students who are aspired to learn GANs. After we give them a short tutorial, they freely used our tool while thinking aloud. I'd like to share 3 key findings with you. First, we observed that participants form hypotheses based on prior knowledge and rapidly test them using GANLab. For example, one participant increased a learning rate to test if it helps speed up the training. Next, users were able to build intuition about the model's training process. For example, GANs have 2 main components called generator and discriminator, but it can be very hard for novices to understand their individual contribution to the training progress. With GANLab, users can train only one of them while disabling the other so that they can more easily observe how each works and how they interact with each other, which can be an important lesson about GAN. Lastly, we observed that participants who are familiar with the literature of GANs found our tool useful for validating knowledge they acquired from research articles. For example, one participant was interested in reproducing a well-known phenomenon called mode collapse. So now we know what users can learn from GANLab. Then we were interested in whether people who voluntarily visited our website can also be actively engaged with GANLab. So we collected 20 weeks of anonymous interaction logs, mostly on click events. Then we identified a list of common actions, which represents a higher level semantics compared to lower level events like clicking on HTML elements. We counted how many users perform each of these actions. I won't show you all the details in this talk, and instead I'd like to give you design suggestions based on the analysis we did for the development of future deep learning educational tools. First, it is important that tool designers take every effort to reduce time for model training. While exploring the logs, we witnessed that some users left the website while models are being trained, especially for those with many layers or neurons that require more time to be trained. It is well known that users do not wait for computer systems if they take much time. We did several tricks, including the use of pre-trained models, but it is a challenging task for deep learning models. Second, we suggest designers provide users with an ability to work with their own data. A lot of visitors played with multiple different data distributions and created new data to work with GANLab. This is also helpful for hypothesis testing. One participant from the observational study created a distribution that is slightly different from a dataset provided by the tool to see how models learn differently. Another participant drew a distribution that looks like a smiling face, which could be a very engaging experience for them. Lastly, we need to consider the fact that this type of deployed tools can be used by people with different expertise and different learning styles. We learned from the observational study that beginners may not have a clear idea of what they can do with a tool. They may be overwhelmed by many features in the interface. For these users, we think it might be more beneficial if we can provide a series of step-by-step exercises which learners can follow instead of providing them with all features. For instance, this is a screenshot of how TensorFlow Playground is integrated into Google's machine learning crash course. The page includes instructions and exercises learners can follow. And the visualizations are versions that disabled unnecessary features for the exercises in this page. I think beginners or first-time users may prefer this type of interfaces, just like distill articles or visualizations designed for the public, such as ones on New York Times articles. Once they familiarize themselves with visualization, they may enjoy one that has a full range of features. To summarize, we present a follow-up evaluation study of GANLab. Through the observational study and usage log analysis, we investigated how visualization tools like GANLab can help people learn AI. We believe tools like GANLab have a huge potential for promoting people's understanding of AI and hope this work will inspire more research from our VIS community. Thank you.
Great talk. Yeah, so it looks like there's no question just of yet, but I can start with a couple. So one question I had
Hi everyone, I hope
while
you're
reading
doing
the paper was that so it wasn't a significant difference, but it turned out that like the manifold part, like the original generation manifold visualization was like the hardest for people to grasp. Like it wasn't statistically significantly more common, but like, do you think there's anything that could be improved? Because like manifolds, like the folding of the space is a quite complex topic to wrap your head around. Do you think there's something to improve at this as well?
Yes or no. I mean, that is the hardest part of GAN. So how generator transforms input noise data into the form that can be taken by the discriminator. So yeah, that is the hardest part. So yeah, that visualization is one of the core visualization of our work, but we found that visualization is still a little difficult for some beginners who have less knowledge on the GANs. So yeah, that's why we thought that we may need to provide some descriptions about some more descriptions about each of the visualization for this type of beginners. So yeah, that's why like we included some discussions on how we can support those beginners, and yeah, probably augmenting with some descriptions for those users might be helpful to for those beginners, I guess.
Okay, great. So I see there's a couple of questions popping up, and I think we still have a little bit of time. Running 1 minute per talk behind, so that's fine. So where are the models actually trained?
Yep. So we developed this GANLab using TensorFlow.js, a web-based JavaScript deep learning framework developed by Google. So everything, including model training, is running on web browsers. So that's one of our contributions of the original GANLab implementation. So that users don't need to using some expensive hardware like GPU to run this model. And I'm seeing that there's another question about like how much flexibility does a user have to change with the model architecture. So in our original implementation, we only support some deep or shallow multi-layer perceptron model, not the CNN or those kind of models, but we support the two different types of loss functions or those kind of thing. And we hope that someone can contribute to open source. This is open source, so probably someone can add some functionality. So, yeah, there's some flexibility, but this is educational tool, so we were not able to support all different kinds of flexibility.
Okay, great. Thank you very much. I think we have to move on. If there's any questions pop up, just write them in Slack, and I'm sure all the authors will still be around. So yeah, let's move on to the next talk, which will be Bluff, interactively deciphering adversarial attacks on deep neural networks. And the presenter will be Haekyu Park.
Hi everyone, I hope you're doing well. I'm Haekyu Park from Georgia Tech. I'm very excited to present Bluff, a visualization tool to interactively decipher adversarial attacks on deep neural networks. Deep learning is now commonly used in many domains. For example, in the medical field, deep learning models can estimate the treatment effects on patients. On the road, we can see self-driving cars using computer vision technologies. However, deep learning models are vulnerable to adversarial attacks. An adversarial attack applies carefully crafted perturbations on data inputs and fools a model into making incorrect predictions. Adversarial attacks jeopardize many deep learning-based technologies, especially in security and safety-critical applications, such as data-driven healthcare and self-driving cars. Due to the threats of the adversarial attacks, people cannot confidently use deep learning models. To overcome the vulnerability of deep learning models, we need to understand how the adversarial attacks permeate the model's internals. Also, for a better understanding about adversarial attacks, it would be worthwhile to examine if and how an attack strength changes how the model produces incorrect predictions. For example, it would be useful to know if a stronger attack exploits the same neurons as a weaker attack does, or if those sets are completely different. We present Bluff, an interactive visualization tool for discovering and interpreting how adversarial attacks mislead DNN into making incorrect predictions. Our main idea is to visualize activation pathways within a DNN traversed by the signals of input data. For given input data, an activation pathways consist of neurons that are highly activated and the most influential paths. Activation pathways represent what features are detected and how those features are related to contribute to the final prediction. To understand how the attacks manipulate the neurons and the paths inside the models, Bluff visualizes the activation pathways of both benign inputs and attacked inputs. That is, Bluff finds and visualizes the most activated pathways given benign and attacked input data. Bluff also visualizes the most inhibited paths by the attack to uncover where the attack is blocking the signals to the benign path. Also, Bluff visualizes the most excited paths by the attack to uncover where the attack stimulates to induce the activation pathways going towards wrong directions. The Bluff interface tightly integrates three coordinate views. It consists of control sidebar, graph summary view, and detail view. Here, a user inspects why a deep learning model misclassifies adversarial giant beta images crafted by the projected gradient descent attack as armadillo. In the main graph summary view, we visualize the activation pathways of benign and attacked input data. Here, each vertex represents a neuron. When hovering over a neuron, Bluff shows the detailed information of the neuron. The detailed view for a neuron shows a feature visualization and example data that visualize what feature the neuron is detecting. For example, for giant panda images, this neuron looks for face of animals that have white furs and dark eyes. Feature visualization is a synthesized image that maximizes the corresponding neuron's activation. Dataset examples are patches of images from the training data that highly activate the corresponding neurons. We also show how the neuron's median activation will change according to different attack strengths. Here in the graph summary view, The neurons are represented with different colors based on their roles. The green nodes are the most important neurons only for the original class, giant panda, which means they are highly activated by benign giant panda images. The blue nodes are important neurons only for the target class, armadillo. The orange nodes are the most important neurons for both original and target classes, giant panda and armadillo. The red nodes are the neurons that are highly activated by only successfully attacked images. These neurons are exploited by the attack to induce the incorrect prediction. By exploring the activation pathways, PGD successfully perturbed pixels to induce the brown bird features, an appearance more likely shared by an armadillo than a panda. Both armadillo and brown birds have small, roundish, and brown bodies. The brown bird neuron then contributes to the armadillo misclassification by activating more features such as scales, bumps, and mesh. By using the options in the control sidebar, users can interactively filter the neurons and connections to visualize. For example, they can select to visualize R graph, or only highlighted neurons, or only pinned neurons. By using the highlight pathways options, users can select which activation pathways to visualize, such as most activated or most inhibited, excited, or most changed by the attack. By using the comparison mode, users can compare how attacks of different strengths have different activation pathways. In summary, we developed Bluff, an interactive system to understand how adversarial perturbations flow of deep learning model. Bluff visualizes most activated, inhibited, excited activation pathways after the attacks, and provides flexible comparison of attack escalation. Thank you all for listening. I'm happy to take any questions.
Great talk. So yeah, I don't see any questions coming up in chat just yet. Well, somebody's typing, but before that comes up, I asked one question. So on your website, on the website that you have linked in the paper, so one thing I noticed, and it's like a very minor thing, like the images, the actual base images, the adversarial attack is based on, I couldn't find them anywhere. Is there a way to actually see them? Like like I felt a little bit disconnected there. I couldn't find.
Thank you for bringing that up. We do not have some features to show that, but yeah, that's a good idea. So let me try adding the images into the interface. Thank you for the suggestion.
Yeah, that would be very cool. And I see some questions are coming up. So is it possible to design robust neural networks?
Yeah, that's a really good question. So this is why we really want to try based on understanding that we gained from our tools. So to design a more robust tool, we are thinking of editing the neural networks. So for example, we know some of the vulnerable pathways that adversarial attack usually exploits. So we are planning to design a tool to allow users to interactively delete some of the vulnerable pathway inside a model. Yeah, but we're still working on it.
Makes sense. So the next question is the pinned view in the interface. Is it a combination of neurons based on specific tests or adversarial images? Is that correct?
Oh yeah. So the pinned view is combination of neuron base. So users can select the users interactively can pin the neurons. It's not pinned automatically by our system. So yeah, if user want to select based on your adversarial images, you can pick that. Yeah, it's all depends on users.
Okay, great. I think I don't see any questions right now. So I think we can continue. And if any questions come up, you're probably around in chat. So let's move on to the next talk, which is visually analyzing contextualized embeddings by Matthew Berger, and presented by Matthew Berger as well. Okay.
Hi, my name is Matt Berger. I'm with Vanderbilt University, and today I'll present my work on visually analyzing contextualized embeddings. Language models, particularly those based on deep neural networks, have made great strides in solving sentence understanding tasks in recent years. As an example, if you look at this question-answer pair with the text passage shown on top and the question on the bottom, state-of-the-art models are capable of taking both as input and predicting the span in the passage that corresponds to the answer, frequency with which elections are held. Prior to training a model for a specific task, many language models perform a process that's known as pre-training, where models trained in large text corpora, absent of human annotations, and supervisory signal is derived from the basic, often sequential, structure of language. A common pre-training task is masked word prediction, where random words are masked out, and it's the model's task to predict what the words should be, relying on the context from surrounding words. Remarkably, through pre-training, models learn quite a bit about the syntactic and semantic structure of language. Accessing this specific language, however, is challenging and represents the focus of our work. Within the NLP community, a common technique for determining the knowledge learned through pre-training is to probe language models for specific properties using human annotated datasets. For instance, given this sentence, we can annotate each word with its part of speech. We may then pass this sentence through our model and obtain for each word what's known as a contextualized embedding, a vector representation of a word that depends on the context of the given sentence. We can then train a discriminative model from these contextualized embeddings, aimed to solve the task represented by the annotated dataset. Parts of speech are just one type of probe, and there are other forms of knowledge that this methodology can be applied to. As an example, named entity recognition. The accuracy of a probe then tells us whether or not a model contains the knowledge that's reflected by the probe. However, there are several problems with this general setup. First, the model that we train might simply be overparameterized and fail to accurately reflect the contextualized embeddings. Secondly, there are issues regarding dataset quality and whether a given dataset accurately represents a particular task. So rather than use supervised probes, we advocate for interactively probing contextualized embeddings. Our approach allows users to explore the knowledge contained in embeddings, identifying general properties of language like word senses, phrase formation, and relationships between phrases to discover finer-grained knowledge that's contained in language models. In analogy with supervised probes, where discriminative models are trained on contextualized embeddings, we take an unsupervised approach, where we'd like to let the data distribution speak for itself. In particular, we first cluster a set of contextualized embeddings using k-means. In this particular example, we show for each one of the words the clusters that were assigned to them through k-means. The corpora sizes we use in our experiments range from 175 to 250k vectors, arising from tens of thousands of sentences, thus providing good coverage and less sensitivity for clustering. Now, the main objective in this work is to help users understand what clusters represent and relationships between clusters. We think of individual clusters as classes, but we don't know the meaning of the classes. So in the example in the above, as an example, for instance, we can identify named entities, specifically locations, while we can also see words grouped into phrases based on clusters that form contiguous spans. Our design is broken up into analyzing individual clusters and relationships between clusters. For analyzing individual clusters, our first view intends to help the user understand different word senses or meanings captured by the embeddings. Specifically, in this view, each row corresponds to a cluster. The X position encodes a percentage of words that belong to a given cluster. The Y position within a row encodes a count of the number of words that a given cluster contains for a particular percentage. This view is helpful in assessing the dependency on context for words within a cluster. For instance, words in the fourth row's cluster are largely context dependent as they largely belong to just that cluster and no others, but there's more variance in word cluster membership in the other rows. Our second view intends to help the user assess how well clusters capture phrases. Specifically, for a given sentence, we form cluster-specific phrases for words that belong to a cluster and then form a contiguous span. We visually encode counts of spans in a heat map, where columns correspond to a particular span length and color encodes a count of the number of phrases. As an example, in our previous sentence, we can group older one and ruined one as phrases of the same cluster with length 2, and then encode this in the heat map for this cluster in span length. We visually encode cluster relationships through co-occurrence counts between cluster-specific phrases in a small multiples plot over cluster pairs. In this view, rows correspond to cluster phrases that appear on the left side of a sentence, where we associate unique glyphs with clusters. Columns correspond to cluster phrases on the right side. The X position within a cell captures the spacing between cluster phrases, and the Y position encodes the number of co-occurring phrases. Spikes in this plot are indicative of recurring patterns of co-occurring phrases within the corpus. We combine these views into a linked and coordinated multiple view visualization, where a user can perform filtering with respect to cluster word membership and cluster span views to inspect individual sentences. Here the user brushes over a region of percentages for a cluster, where linked highlighting between both cluster word memberships and the co-occurrence view highlight which clusters overlap in terms of their memberships. A similar form of filtering is supported for cluster spans, where the user can limit cluster-specific phrases to a range of spans. Upon clicking a particular cell, a more detailed view shows on the bottom with the pair of clusters highlighted underneath the phrases. Here we can see that the user's selection corresponds to titles, more generally noun phrases, of named persons. Here we show a use case of our interface for exploring context. The user first brushes the cluster word membership view near percentage of 1, thus selecting largely context-independent words. By then selecting a cluster pair in the co-occurrence view, we can then see that this cluster largely corresponds to nouns. Next, by performing a selection that's more context-dependent, we can see other clusters being highlighted. In particular, we see a spike in a particular cell for a different cluster that happens to share words with the brushed cluster. Looking at its example sentences, we can see that these words can be treated as adjectives or compound nouns, indicating their reliance on context. In this example, we show how the user can use our interface for phrase discovery. By limiting phrases to be at least of length 2, the user can then select a pair of clusters and inspect example sentences. Here we find that this cluster captures the concept of time-based phrases. So in conclusion, we've presented an approach for interactively probing language models by exploring their contextualized embeddings. Our approach is similar to supervised probes, but rather than build discriminative models, we instead employ clustering and then explore the resulting clusters in terms of a visual interface. And we study the basic statistics of language, like spans, co-occurrences, as a way to help discover cluster properties and relationships. For future work, we plan to employ a more thorough user study. So we want to see if linguists or the general public can use our interface to help identify patterns. We also want to extend our approach to model comparison, so employing embeddings from different model layers, as well as comparing across models. Thanks.
Great talk. Yeah, so let's ask some questions. I don't see any in chat yet.
Hi,
so
I'm
let me start. So one thing I was wondering about was you're using k-means for clustering. So what determines the number of clusters that you're looking into, and also did you look into other clustering methodologies like linkage-based clustering and how that might change the results? Since k-means is always very compact sets in this space, and clustering can also form strings and stuff.
Right. So that's a good question. So with k-means, we tended to over-cluster as a way to better capture as much fine detail in any type of linguistic properties as possible. We find so k-means is fairly robust because we're clustering over a large number of vectors. So we have a total of order of hundreds of thousands of vectors. So k-means ended up being fairly robust, giving us pretty consistent patterns across different initializations. So we didn't end up exploring different types of clustering methods as a result.
I see. So I have a follow-up question to that as well, actually. And so that is, so what about not doing the clustering, but letting the user select, let's say, words that they want to group together and seeing maybe if other words pop up in that as well. For example, I want to get nouns. I click on 3 nouns, and the system can come up with, like, oh, here are other nouns that we identified.
I see. Yeah, that's a very good, interesting suggestion. Yeah, so I think that you could probably, by selecting a particular word, you can then look to see what are, maybe it's nearest neighbors, or do some type of density estimation to have a way of assessing, well, what are similar words like that as a way to drive the interface. Yeah, that's an interesting idea.
Okay, cool. I don't see any further questions, but like if some might pop up, so please stay in chat. And yeah, thank you again. And let's move on to our next talk, which is, one second. Oh, I jumped the line here. I'm sorry. So here we are explainable spatial clustering, leveraging spatial data and radiation oncology, and it will be presented by Andrew Wenzel.
Hi, I'm Andrew Wenzel, and I'm going to be talking about our work in visualizing and exploring spatial clusters based on our work with anatomical data from cancer patients that received radiation therapy. This work was done in collaboration with the MD Anderson Cancer Center and the University of Iowa. In cancer patients, the tumor location and disease spread are vital in deciding optimal treatment and forecasting patient endpoints. Radiation to tumors puts nearby organs at risk, and different patterns of disease spread play an important role in how the patient responds to therapy. One of the most important applications of machine learning to cancer research is the clustering of a patient cohort into groups associated with different risk factors. This application is known as patient stratification. However, clustering methods typically do not account for spatial data. In our case, head and neck cancer researchers are seeking a clustering method that accounts for the patient's spatial disease spread. Despite a widespread interest in spatial clustering techniques for patient stratification, their adoption in healthcare is stifled by the difficulty in understanding the inner workings of such methods. During a multi-year, multi-site project, we dealt with a large number of patients treated at the MD Anderson Cancer Center. We aimed to find patient clusters based on the important underlying anatomical structure of the disease spread. Despite a lack of computational methodology for this kind of spatial similarity, our spatial clustering method needed to consider many unique disease spread patterns and account for symmetry in the head. Furthermore, we experimented with different numbers of clusters and ways of determining cluster membership. Our methodology leveraged a period of participatory development to create a broader deployment as part of this multi-year project with evolving requirements. The paper describes several contributions related to, first, the collaborative visual design process during the development of a spatially informed clustering model. Second, to visualization design to help explain these clusters to clinical audiences during model deployment. And, last but not least, several design lessons for visualizing clusters with spatial data. Other work has been done in visual cluster analytics, but these methods don't consider spatial cluster data. Work has also been done in visualizing anatomical cohort data and developing clinical models, but don't discuss spatial clusters or designing for broader audiences. During the clustering model construction, we mapped the disease spread to the anatomical spatial data. We followed a graph theory-based approach and encoded symmetric cases on the same underlying graph. In these encodings, purple and green denote the disease spread on the left and right side of the body, and can be combined in the same compact graph representation shown last on the right. We arrived at this representation through multiple design iterations described in the paper. A variation of this graph visual encoding was used in an interactive interface to assess different spatial similarity measures, and then to explore different clusterings and cluster membership as part of a dendrogram. This graph-based encoding is a compact visual representation of the disease spread in patients. It accounts for symmetry and is aligned with the graph theory we used to calculate similarity. This representation also supports comparison and clustering. However, since it is abstract and complex, it was difficult to interpret by other clinicians who did not participate in our design process. It also gives more emphasis to the modeling approach and less emphasis to the toxicity outcomes and correlates. For the deployment model, we started with a simplified anatomical map of the disease spread in the head and neck. From this map, we created a cluster representation for each cluster, in which we heat mapped the percentage of cluster members with affected nodes in a particular region. Finally, we added a radial visual encoding to show clinical correlates and toxicity. Again, we arrived at this representation through multiple design iterations described in the paper. The advantage of our deployment model was that it was easier to distribute in print as a static figure. It was also based on anatomy, and so it was easier to interpret by broader audiences. It also shows correlates with clinical variables and toxicities. However, the added complexity of this design would make it costly to use during model development. Throughout the course of this project, we have identified 5 design lessons. First, use visual scaffolding based on the user's background. During model development, we found that a graph metaphor worked best, while during deployment, clinicians in the wider audience preferred a frontal, butterflied, anatomical map of the neck that was used routinely in radiation oncology. Incorporating additional details for our clusters was essential to the user activity. For example, during agglomerative clustering, dendrograms with labeled leaf patterns helped identify how the clusters merged and split. Including secondary and potentially confounding variables helped mitigate situations where the clinical readers inferred direct causal relationships between clusters and outcomes. As our project progressed, we shifted from interactive visualization for a small audience towards static figures used in papers for a much broader audience. We wish our initial design anticipated broader audiences than our collaborators. Finally, we found that decision trees and other white box classifiers were useful for explaining the differences between clusters. This talk reflected on the process of designing visualizations for clustering with anatomical spatial data. These designs were developed in 2 phases over several years using participatory design alongside cancer clinicians and data mining scientists. In the future, we hope to incorporate additional insights from sibling projects and develop a more comprehensive set of design guidelines for spatial cluster analysis. Whereas here we focus on a specific project, our stratification approach and our design lessons can be generalized to any type of spatial cancer data. We would like to thank all members of the Electronic Visualization Laboratory, members of the MD Anderson Head and Neck Cancer Center, and our collaborators at the University of Iowa and our funding agencies. Thank you.
Great talk. Yeah, so I don't see any questions right now in chat. I saw some people typing, but they gave up, unfortunately. But I have a couple of questions before we move on. So one question I had when reading the paper, you mentioned quite in multiple instances that people confused whether they were seeing a single person or a cluster. So do you have any insights on that and how to mitigate that issue?
So I think our second design iteration, we use the heat map. And since those aren't binary, I think that helped a lot. The confusing clusters with people was closer to the first iteration where we tried to show like hierarchical clustering. And I think, so the kind of using continuous values like that helped a lot. I also think at some point you just have to explicitly label everything. Because in that review process for the first one, you kind of just had to keep adding labels. Yeah, or having some kind of distinct design differences between the individual people and the clusters if you show them at the same time.
Yeah, that sounds great. I see a couple of people typing. Hopefully the questions come up. Otherwise, oh, okay, there it is. So who is the actual target user for this visualization?
Oh, so I think the general category is medical researchers. We basically work with people at a head and neck cancer center, and their main goal is kind of just to find ways of creating better like treatment recommendations and forecasting. So the target audience is first them to kind of get those insights, and then when we disseminate, we try to aim at papers for clinical oncologists. So yeah, mostly clinical oncologists that are more research oriented, I guess, since they would want to actually look at the more detailed insights we have.
Mm-hmm.
Yeah.
Sounds cool. Okay, great. So I guess maybe people have more questions coming up. I see people typing, and so maybe there will be questions coming up during the next talk. So please stay in chat and tend to those. But thank you again, and let's move on to the next talk, which is ProtoViewer, Visual Interpretation and Diagnostics of DNNs via Prototype Factorization. And presenting will be Hyun-Han Chau.
Hey everyone, I'm Hyun-Han Chau, a PhD candidate at Purdue University, computer graphics major, and a research internship at Bosch Research North America. Here, we are presenting our recent research, ProtoViewer, using factorized prototypes to visually interpret and diagnose deep neural network. This work is co-authored by research scientists at Bosch, Zhen Dai, Dr. Panpan Xu, and Dr. Liu Ren. Along with the growth of successful implementations of deep neural networks in different domains, the request of providing trustful interpretabilities to the model outputs and reliable diagnostics while training the neural networks and models has been raised. There are two motivations for this research. First, in practice, the difficulty of adopting a deep learning model is because of the lack of interpretability. Second, developing deep neural network model is often costly because of the lengthy diagnostic process that requires the users to understand more about DNN models. In general, interpretable machine learning approaches can be categorized as intrinsic explanation and post hoc way. Intrinsic explanation often utilizes built-in explanation mechanisms, while training as an inherently interpretable model. In contrast, post hoc approaches interpret the machine learning model and outputs after training. Researchers have been studying both areas. Methods like ProSynite and Retain VIS, introduced in early days, are injecting additions to the original models and observe the variations while training the models. For post hoc approaches, global methods like SUMMIT, TCAF, and CNN-VIS visualize the activation outputs and model space globally, while local methods like GradCam and LIME are applying local attentions by either computing gradients or injecting perturbations. Additional algorithms like SmoothGrade and SHAP are also showing some promises. In our research, we focus on developing a post hoc model diagnostic interpretations and visualization technique, which could provide guiding insights while the users are developing or about to deploy popular DNN models to their practical usage scenarios. To provide practical and trustable explanations for the model diagnosis, we identified the following high-level requirements for framework development. First, faithful to the original model. Otherwise, the results could be the artifacts from the interpretations algorithms instead of the original model. The explanation should reflect the model's behavior in an authentic manner. Secondly, provide global explanations. While local explanation methods can provide insights into models' underlying operations, it can be limited to explain only one or a few instances at a time. Thirdly, support comparative analysis. For model diagnosis, it's critical to understand the model's behavior on different subsets of the data. Our research contributes to three aspects: a framework for post hoc diagnostic interpretation and diagnosis of DNNs through weighted combinations of prototypes. Second, a visual interface that summarizes model behavior through prototypes and their corresponding weights on different subsets of the data based on user specifications. Example user scenarios on two popular DNNs for image classifications and two different image datasets. We first introduced our pre-proposed proto-fact algorithms for factorizing global prototypes. A given convolutional neural network, the algorithm first randomly collects prototypes candidates, which are image patches collected from the training data. Then the algorithm decomposes a user-suggested activation layer. Proto-fact will decompose the matrix into two matrices, with the user set K as the amount of prototypes in total, namely the weight matrix W and the prototype matrix H. In matrix H, each row represents a flattened prototype, and in W, each entity in the row encodes the corresponding weights for each prototype. The high-level idea of the algorithm is building a surrogate model by decomposing a selected activation layer into a combination of prototypes and their corresponding weights. The objective is converging the difference between the model predictions from the surrogate model and the original model. In other words, let the surrogate model mimic the original model predictions as close as possible. Then, we try to interpret the original model behaviors via the completed prototypes and their weights. Through the meaningful image patches, we are able to interpret the training images. For instance, a car instance can be represented by the prototypes like car wheel, headlight, and trunk. Our experimental results show the high fidelity of the surrogate model to the original model given proper setting K and the activation layer for factorizing. There is a trade-off between the increased computational cost and more prototypes and a small discrepancy. Here are the design objectives. First, provide an overview of the model behaviors with prototypes. Second, support the comparative analysis of prototypes using different subsets of data. Third, visualize a fine-grained performance matrix to pinpoint the region of error and have the user select the subsets of the interest for further analysis. Fourth, support the grouping instances with a similar prototype's weights for cluster analysis. Finally, visualize the instances with the highest weights on each prototype for detailed analysis. This slide shows our user interface overview. ProtoViewer consists of multiple visual components to serve the analytics. First, a prototype overview showing the average prototype weights for instances from each class. It also includes an expandable panel to display the prototypes and a slider to selectively display top K prototypes for each class. A confusion matrix and a series of stacked bars to visualize the summary statistics for common misclassifications and the predictive performance for each class. A control panel for selecting the parameters like a dataset, the model, the factorized layer, and the number of prototypes. In the end, a detailed pop-up view can focus on the prototype and check the details of each instances with the highest weights on that specific prototype. Here, we demonstrate two usage scenarios. We first use a prototype to examine the results from applying ResNet to fashion each dataset. The user first observes the fact that many scandal instances are wrongly predicted as sneakers. By clicking on the corresponding cell in confusion matrix, an orange error graph is visualized the weights of top 15 prototypes computed from all correct predictions class scandals in prototype view. Clicking the cross button, the user can check the top 15 prototypes. Targeting the subset of incorrect predictions, the user can observe a spike triggered by a sneaker prototype. The user clicks on the sneaker prototype. The pop-up window shows the details of all incorrect predictions, weighting highly on this sneaker prototype. We can find that all these instances are those scandals with the solid backstay parts on the shoes, while the correct ones are showing the clear hollows. The other example is showing when a user diagnoses the results from applying VGG19 to CIFAR 10. With a similar diagnosis strategy, we can find some insights like, for those plane instances which are incorrectly predicted as ships, they are often water planes. In the end, we conclude that the ProtoViewer contributes to a framework for post-hoc model diagnostic interpretation and diagnosis of DNNs through weighted combinations of prototypes. There are a few future works that we think we can further investigate to help the users to better understand the deep neural networks. Thank you for your listening. Have a nice day.
Great talk. And I already see, I see a question already in chat. So let's get right to it. So the question is,
hello.
One big challenge in XAI is evaluation. I wonder if the authors have thought about how we can evaluate whether extracted prototypes are good representatives of datasets.
Yeah, really good question, actually. So we have been thinking about that from a very practical perspective, because I think this is a main sort of a topic when we are debating whether interpretable machine learning, especially visual analytics works, are useful for improving machine learning in this kind of field. So regarding those prototypes, so we're thinking that can summarize different sort of like subsets, and the researchers has proven that if you have a more, let's say, finer grain labels probably, or details about the data, that you can have a better, you may receive better like prediction accuracies or results. So I think that would be the one solution. The other solution is more like when we can sort of like revisit the model that we are using for training, and we can look at the model sensitivities, to different sort of classes. And in that case, we may be able to find good solutions. So the question, these are the answers for this question, but this is the ongoing actually further investigations from our side as well.
Very good, very good, very cool. Yeah, very interesting work, and yeah, looking forward to hearing more. So I guess unless there's more questions coming up in chat, probably we can move on to the ultimate talk, the last talk today in the session. So yeah, thank you again, and let's move on to the next talk, which is instance flow, visualizing the evolution of classifier confusion on the instance level. And it will be presented by Michael Püringer. Yeah.
Hello and welcome to my presentation. My name is Michael Püringer and I'm a master's student at Johannes Kepler University Linz in Austria. I'm going to present our work on instance flow, a tool for visualizing the evolution of classifier confusion on the instance level. This is joint work with Andreas Hinterreiter and Marc Streit. When training modern machine learning classifiers, such as neural networks, we often rely on the progressive improvement of specific metrics, for example, classification accuracy, recall, or precision. The most common way of visualizing this progression on a global level are simple line charts. But for specific tasks, such as multi-class classification, these are prone to hide important factors such as inner-class confusion and instance-level details. Related work on visualizing instance-level information has mostly focused on model-dependent parameters, such as the activation of neurons in response to a given input or the behavior of individual layers of a neural network. Similar visualizations exist for GANs and deep Q networks. Likewise, visualizations focused on the performance analysis of classifier typically do not enable a true temporal analysis. And additionally, most visualizations rely on the aggregation of instance information, such that instances are not directly accessible for further inspection. Previous work from our group is Confusion Flow, a visualization tool allowing to access temporal metrics on the class level. The paper was recently published and is also presented at this conference, so make sure to join the talk given by Andreas. The temporal analysis is done by extending the widely used confusion matrix with a temporal aspect, showing aggregate scores such as accuracy in a heat map or line chart encoding throughout the epochs. By stacking different datasets vertically on top of each other, different classifiers or runs and their evolution per class can be compared easily. As a next step, and with the need of accessing specific instances directly, we built and now present Instance Flow. The interactive visualization tool allows machine learning experts to inspect individual instances and their predicted class labels throughout training epochs. Instance Flow consists of two main views, the flows view on the top and the instance ranking view on the bottom. The flows view visualizes the classification of the individual instances throughout the epochs using different aggregation levels. The ranking view on the bottom shows each individual instance and allows for a detailed inspection, including 3 metrics we defined for this paper. Instance Flow was built to answer specific questions regarding the identification of difficult or oscillating instances, tracing an instance's classification history, or assessing class distribution and its changes throughout a given epoch range. In the following example, we're looking at a classification of the CIFAR10 dataset. First, we start within a specific epoch. Here we see a box enclosed by purple dotted lines, which represents a prediction as cat. Within this container, the distribution of the real labels of the instances is shown. We then extend this for all selected classes, in our case dog as blue and deer as orange. Predictions as the other 7 classes are shown in the gray box in the center. Horizontally, we then show the same visualization for a selected epoch range. Within each of the prediction classes, we can see the distribution of the real labels of the instances predicted as such. To better understand the movement of instances throughout the epochs, Sankey diagrams are used to visualize the movement of instances from one class to another. In this case, many deer instances colored in blue were incorrectly classified as any of the non-shown classes in epoch 20. The Sankey diagram and the distribution of deer instances in the next epoch show that nearly half of the previously incorrectly classified instances are moving to the correct class. To avoid visual clutter, the distribution boxes can be hidden in favor of the flows, as the flows implicitly encode the distribution per prediction class. In the previous views, the instances were aggregated and shown as distribution bar chart or flows. The level of detail can be modified such that within each class prediction box, the actual underlying instances are shown. Each of these instances is encoded using glyphs, which indicate the stability in the current epoch of the instance. If specific instances are of interest, the corresponding classification paths can be traced, with correct and incorrect movements colored as green and red, respectively. Again, the Sankey diagrams can be shown, and they automatically highlight the included instances on hover. Clicking on this selected flow highlights the classification traces of all included instances. Below the previously described flow visualization, all instances are organized in a sortable, filterable, and flexibly customizable ranking using the lineup ranking technique. Each row contains a single sample showing the image for image classification tasks, as well as the ground truth label including color coding. Next, the prediction labels throughout the epochs for this specific instance are displayed as a colored heat map. To answer certain questions, such as which instances are visiting many different classes, which are oscillating between classes, or which instances are specifically hard to classify, we introduced three metrics. The frequency is the ratio of epochs in which the previous prediction is different to the current prediction. The variability is the ratio of how many classes in total were predicted for an instance across all epochs. And finally, the misclassification score of an instance is the fraction of epochs in which it was assigned to the wrong class. In the ranking, each row can be condensed to a few pixels to summarize and easily identify patterns. In our case, the condensed view of the prediction distribution reveals a pattern of successful learning, as the number of correct predictions, in this case purple on the top and orange on the bottom, become more dominant over time. To summarize each class with its instances, the aggregated view shows a histogram of all predictions. It immediately shows that the own class is predicted the most, but also reveals class confusion between cat and dog, for example. So with that, I would like to conclude this presentation. There is a link to the GitHub repository, which you can follow to find the full paper, these slides, an online demo with preloaded datasets, and the code implementation. Thanks for listening, and I'm happy to answer any questions.
Great talk. So let's wait a little bit until the questions come up. And in the meantime, I have a question myself first. So my question is, like, what instances are you displaying? Are you displaying the training instances or the instances from the test instance, from the test set, or from both? Because like each of those have like different implications of how to interpret the visualization.
Yes, so you can do anything you want. You can also load new instances if you want to. We really tried to build a, let's say, model agnostic tool. So you're not forced to use the test set instances, training set instances, or you can use anything you want. You basically just have to upload your prediction classes for each instance.
Okay, and also like over time, basically, like do you keep like snapshots of the model?
Yes, you can, for example, save snapshots for the model for each epoch or every 10 epochs, and then just save them and upload them to the to the instance flow instance.
Very cool, very cool. I think that is a question. It's quite bold to claim that each row of the bar charts can be reduced to a few pixels. What evidence can you give to support that claim?
Yes, that's true. So we have the problem that when training modern, for example, neural networks, you're working with many instances, with hundreds of thousands or millions or even more instances. It's quite hard to kind of find an aggregated way to show all of them. And reducing them to just a few pixels kind of gave us an opportunity to find that cool visualization. We can see how the progression over time evolves. So yeah, it's quite bold to assume that we can reduce every instance, but this is just the most aggregated view we can offer.
Very cool, very cool. And there's another one. So are there ways to filter down which instances are shown in instance view? Mostly thinking about how this scales to larger training data.
So we have the possibility to link both visualizations. So you can either show only the selected instances in the flow visualization or all of them. And there's also the filtering in the ranking, which automatically adjusts the flow. So the thing is, the flow does not handle very large data sets, of course. That's why the ranking is there. So in the ranking, you would filter for specific instances and then view their visualization over time.
Cool. Yeah, great. So I guess, oh, wait, no, but there's not evidence. Okay, well, we can continue the discussion in chat. I think there's more to be talked about. But yeah, thank you so much. And I guess that concludes our session today. And thank you all the presenters. Thank you again for presenting your work and standing here to answer the questions, and also for chat to providing those questions and the great discussions that we have in chat. Yeah, so, but with that, I think that is the end of the session. So thanks everyone. Bye-bye, have fun.
We propose data-driven space filling curves. Our new method generates linearizations that better preserve coherency than existing techniques. Our method supports 3D datasets and even multi-scale data on a quad tree or an octree. Many visualizations benefit from our method. For example, visualization of multivariate particles and visualization.
In this work, we conducted a design study with clinical researchers to develop a visual analytics application for exploring disease progression pathways. As a result, we developed VIS, which seamlessly integrates hidden Markov models with interactive visualizations. The usage scenario and user experiences demonstrate the usefulness of the application to gain useful insights out of disease progression trajectories in a transparent manner.
In cancer research, it's useful to group patients based on disease spread patterns to the lymph nodes. But once we create a new clustering methodology using spatial data, how do we explain spatial clustering to non-experts? In this multi-year project, we dealt with both a participatory design stage and a broader dissemination stage, and distilled specific lessons for interpreting spatial clusters.
There are many similarities between visual analytics and interactive optimization. The design of visual interfaces for optimization systems is an application of visual analytics. However, many optimization systems are automated. If you are thinking of building an interactive optimization system, come to our talk. We have prepared some tips for you.
We miss you, indeed. We miss you being in New Orleans. We also miss doing what New Orleanians so often do best, welcoming you to our city, telling you about our favorite places, and watching you truly experience the absolute beauty and indescribable magic of this incredibly special place. Everything that you know and love about New Orleans is not only here waiting for you, but it's better than ever. We have been busy getting ready for your arrival and have considered every detail of your visit with world-class dining, a brand new airport, new museums and attractions, and hotels to fit your every need and desire. Our world-class convention center is completing a beautiful new pedestrian park and is beginning renovations to other facilities. We'll even have gumbo on the stove, and our musicians are tuning their instruments. So when it comes time for you to return, we'll welcome you back to our table and celebrate with you our 300-year-old traditions. And we know that you will create new ones along the way.
Good morning, New Orleans. We love you, New Orleans.
Just know that we're thinking of you here in the Crescent City, and we can't wait to see you soon.
Love New Orleans. When people come, they never leave, because we're swinging that way. The sun shines so bright. The breeze is so nice.
Given a dimensionality reduction scatter plot, we project its original subspace. Through the orientation and shape of our glyphs, both the global trends and local patterns can be identified. To transform the vectors, we use implicit function theorem. We apply our method to different kinds of data.
Visualizing the performance progression of machine learning techniques is often achieved by plotting the accuracy in a line chart. For specific tasks such as multi-class classification, they hide important factors such as inner-class confusion and instance-level details. We propose Instance Flow, a tool for interactive visualization of the evolution of classifier confusion on the instance level.
Region-based vortex measures are commonly used to extract vortices. The ideal threshold to extract the vortex boundary, however, varies spatially. To detect vortices without manual thresholding, we utilize supervised deep learning. For the regression, we evaluate 3 recent network architectures. The resulting networks are able to detect vortices that grow in size due to diffusion, despite their angular momentum becoming smaller.
How do user interactions lead to insights? We present a case study with a tool that supports 5 types of interactions for exploring drug-target relations. Through an evaluation, we collected interaction trails, manually extracted interaction patterns, characterized the user insights, and explored the relations between interactions and insights.
We introduce a direct volume rendering approach that can render encrypted images directly from encrypted datasets. The rendering is performed by operations in the encrypted number space which are dual to operations in the plaintext space. Therefore, the rendering system does not need to decrypt the data. This homomorphic volume rendering approach makes it possible to use untrusted servers for rendering without compromising privacy.
Hey everyone, I'm Junhan Zhao, a PhD candidate at Purdue University, computer graphics major, and a research internship at Bosch Research North America. Here, we are presenting our recent research, Viewer, using factorized prototypes to visually interpret and diagnose deep neural network. This work is co-authored by research scientists at Bosch, Zhen Dai, Dr. Panpan Xu, and Dr. Liu Ren.